Welcome to Lecture 7. This is Section 6.2 on volumes. So in our last section, in 6.1, we learned how to find the area of a region bounded by curves. So we can find the area of a space. And in this section, what we want to do is we want to take that space and we're going to rotate it around some kind of line, typically an axis, or it could be a line y equals a or x equals a. And that's going to create a solid for us, right? If you spin something around in a circle, it creates a solid. And I'm going to post a video so that you can see an animation of that so that's a little bit clearer. And what we're going to do is we're going to use the same thing we did with area. We're going to, in Riemann sums, we're going to use to approach this, okay? And you can see I filled a little bit of this in, but I'll show it to you in a second. But what we're going to be thinking about is that if you have a solid of revolution, you can slice it into thin either discs or washers here. And I'm going to show you this in a second. So discs or washers, each with an area function a of x. So we're going to find the area of that space. And it has a thickness, right? We're going to call that our dx. And then what happens is we cut them so tiny that we take infinitely many of them, just like we did with our area and our rectangles, to find the volume of the cross section, okay? And so what that looks like is something like this. So think about if we were to take this line here and we were to revolve that area around the x-axis, we would get a solid that looks something like this, right? And if I think about cutting that into a cross section, it's going to have something that looks like this, right? And if I slice it infinitely thin, think like sandwich meat slices, right? Then I have kind of a little disc in there, okay? Now you get a washer is if you end up with two functions. So I can take, let's see, this function, and they create kind of a little banana or oval shaped thing there. And we're going to revolve that around the x-axis. And if I do that and revolve it around, I'm taking this space and revolving around. So when I cut into it, my cross section is now a washer because I don't have this space in the middle. Okay. And so what we want to do here is we want to be able to find these volumes. And so if we think about doing this in the same way we did our Riemann sums for our rectangles, I'm going to have infinitely many of these little circles. So instead of having heights that I multiply by dx, the thickness dx, I'm going to take these cross-sectional areas times an infinitely small width, right, which is our dx. So what we're going to do here is we're going to define our volume, and I don't want to do that. We're going to define our volume of the solid to be the following quantity, okay? So think about this for a second. If for my discs, I have essentially a circle here, right? And so the area, the cross-sectional area here, we're going to call A of x, right? So what we're going to do there is find the area of this circle. And you know that the area of the circle is pi r squared. Now, if you think about the radius of my cross-sectional circle here, here's the middle. The radius goes out to here. And that's actually on my curve. So the radius of my cross-sectional circle is actually the function. So what we end up with here is that our cross-sectional area is pi r squared, but it's actually pi times the function squared. Okay. So that when we go to find the volume, we're going to take that times an infinitesimally small thickness, dx, and integrate it over the boundaries, okay? Because in theory, I've got boundaries here, right? This one is from 0 to whatever this x value is, right? So let's call this from A to B. And that means that my area, or the volume, will become pi times the integral from A to B of my function f of x squared dx, right? So I took the cross-sectional area times the dx. I just pulled the pi out front of the in the integral, and I added them, and we found the area under the curve, just like we did with Riemann sums, okay? Now for washers, so this is for disks, right? Meaning there's no holes in the middle. For washers, what you want to think about is that really what I'm going to do to find that small space is I'm going to take the larger one and find its volume, right? So this is the larger one, and this is the whole volume in here. Let me switch to this. There we go. So I want all of this volume right here. And then to get just this little space inside, what I'm going to do is I'm going to say, okay, well now let's take the inside radius one and revolve that one. And that's going to give me this area here. And if I kind of overlap these, let's see if this will actually work. Oh, wait, don't take that. If I see how good my picture is. Not great. If we take out that blue region, you can see that the remaining yellow region is what I have in my picture. Okay, and so if I take the volume for the outer and subtract the volume for the inner, that gives me the volume of the washer that I want. Okay, well, we just said that to get the volume of this one, we would take pi, and let me write it down here. So our total volume is those two subtracted. So the first one is pi times the integral from a to b of our outside radius. So I'm going to call that our RW squared dx minus, because we're going to take away that interior volume, pi times the integral from a to b of our inside radius squared dx. And then, of course, you can pull that pi out front. And I'm going to leave the R0, the RO, and the RI in here because we're going to have to, I'm going to combine the integrals here as well. Okay, and because we're going to have to figure out what those radii are, and they're typically functions. Okay, and we'll tackle that using our examples.